Okay, so now we come to the beginning of game theory. So now we're going to see the definition of what's called a normal form game, which is one of two main formalizations of what it means to be a game in game theory. The other one is called extensive form, and it's going to be covered in weeks 3 and 4. Normal form is going to be covered in the rest of this week and next week. So let's see the general idea. So in normal form games, we have some number of players and they're all going to make choices simultaneously. So an example of this is rock, paper, scissors. So when two players play rock, paper, scissors, they simultaneously throw hands. And in that case, it really is simultaneous in the sense that the two players move at the same point in time. But really, the conceptually important thing is simultaneous is about information. So the players can move at different points in time as long as neither has access to the other one's choice, as long as it's hidden information. So they're kind of morally simultaneous. And then after the players make choices, they're all going to get a payoff. And the payoffs for every player are going to be determined by the choices of every player. So what that means is that players are going to have to mutually reason about what each other are going to do. So this is kind of the basic idea of game theory, is that we're in these kind of circular situations where everybody's payoff depends on everybody's action. So everybody has to circularly reason about what everybody else is going to do. The name normal form is a little bit of a strange name. I also sometimes call them just simultaneous games. The reason that these are called normal form is that any more complicated type of game can be converted into a normal form game, which is equivalent in some sense. So a normal form game is a kind of reduced form. So that's where the name normal form comes from. And we'll see this again in a couple of weeks. So here's what a normal form game is mathematically. We have some number of players, and then each player has some number of choices. And then we have a payoff function that says for every combination of choices by the players, so this thing is notation for the set of n tuples of choices. So this is a choice of a move for each player. We get an n tuple of payoffs, where the ith one of these is going to be the payoff for the ith player. So normally, for example, in machine learning, you will have a single real number that's the outcome, like the loss or whatever, or the objective. But so game theory, this is a fundamental difference of game theory to other forms of optimization, is that we don't get a single real number outcome. We're going to get one outcome for every player. Equivalently to this, we could also say that every player has their own individual payoff function, which says that for every n tuple of choices by all the players, that player J gets a payoff. Okay, so that's a whole bunch of maths. So what does this actually mean? So when we have two players, these things are particularly easy to visualize because you can draw these things as a matrix. So for example, here's a matrix representation of rock, paper, scissors. So here we have two players, and both players have three choices that they can make, called rock, paper, and scissors. And so we can make this grid where the moves for player 1 are in the rows and the moves for player 2 are in the columns. And then, so each of these 9 grid squares represent one of the possible tuples of a choice made by each player. So there are kind of 9 possible combinations of things the players can do. And then we need to give for each of these, we need to give a pair of real numbers. So here there's a subtlety which connects back to the previous video. So in rock, paper, scissors, the 3 things that can actually happen are win, lose, and draw. But here we're encoding them as real numbers, namely a win is being encoded as +1 and a loss is being encoded as -1 and a draw is being encoded as 0. And here we're actually, so crucially, we're making a modeling choice when we do this mapping of win, lose, and draw to numbers. Namely, for example, this says things like, if we had the choice between draw with certainty or win with probability 50% and lose with probability 50%, we're indifferent between those. So that's an additional piece of information, and there's a whole bunch of other kind of combinations like this. All of this information is not part of the rules of rock, paper, scissors. This is part of our model of the preferences of the agents playing rock, paper, scissors. So you see this kind of subtlety of what's happening when we encode outcomes as real numbers. Okay. And hopefully I've got this matrix right, and you can see that, for example, paper beats rock. So player 2's playing paper and player 1's playing rock, then player 1's getting a payoff for -1 because they lose, player 2's getting a payoff for +1 because they win. Okay. In the next video, there's going to be a whole list of examples. Okay. The other kind of basic fundamental concept with normal form games is strategies and strategy profiles. So a strategy strategy in game theory means something like a plan for how the player is going to choose their moves. And a strategy profile is going to be a strategy for each player, a tuple containing a strategy for each player. There is traditional terminology, which is that a pure strategy means a deterministic strategy, and a mixed strategy means a probabilistic strategy. So this kind of, do you allow your players to use randomness while choosing their move or not? And for a normal form game, choices are simultaneous, which means that players have absolutely no extra information available while they're choosing their move. So what that means is that for a normal form game, a pure strategy is the same thing as a move. So a plan for how to choose a move, if you're not allowed to do randomness, is just a fixed move. That's the only thing it can be. So note that this is specific to normal form games. So when we have more complicated classes of games like extensive form in a couple of weeks, we're still going to have things called strategy, but they're not going to be the same thing as moves anymore. Because players are going to have the ability to do other things like make observations of the game state. Okay. So a pure strategy is just an element of that player set of moves. And a pure strategy profile, which is going to be a tuple of a strategy for every player, is going to be just an element. So it's going to be a tuple, a choice of move for every player. A mixed strategy, on the other hand, is going to be a probability distribution on the set of moves. So a kind of a strategy to choose a move, if you're allowed to do probability, is exactly a probability distribution on your set of moves. Okay, and a mixed strategy profile is going to be an element of this thing. It's a tuple consisting of a probability distribution on each player's moves. So crucially, in a mixed strategy profile, all of the players are randomizing independently. So every player has their own independent source of randomness. That turns out to be kind of important later. So just like you can visualize probability sets of probability distributions, you can also visualize mixed strategy profiles. So for example, if we have a two-player game and both players, so player 1 has moves A and B, and player 2 has moves C and D. So here I've written player 1, x1 equals AB, x2 equals CD. The set of all of the mixed strategy profiles for this thing, you can visualize it as a square like this. So along this axis, we have the probability distribution for player 1 with 100% A here, 100% B here. And along this axis, you have distribution for player 2 with 100% C here, 100% D here. And so for any point in the middle, you can project it onto the two axes and to read off what are the probabilities for the two players' moves. So this point in the middle, for example, is both players flip a coin. So both players choose one or the other move with 50-50 probability. This point here, this says that player one is flipping a coin between A and B, but player two is always doing D with probability 1.